Helicopters are the only machines on Earth that can lift straight up into the air, hover motionless, fly backwards, sideways, or rotate in place. They rescue the stranded, patrol the skies, move soldiers, deliver supplies, and reach places no airplane ever could. But these remarkable aircraft are also some of the most complex machines humans have ever built. A single rotor system can contain more than 10,000 individual components. A tiny imbalance of just a few grams can shake the entire aircraft apart. Today, we step inside an advanced aerospace assembly plant, a place where aluminum, titanium, carbon fiber, and engineering ingenuity come together to create helicopters capable of saving lives and defying gravity. And later in this film, you'll witness the most delicate and critical moment in helicopter assembly: the rotor balancing sequence, the test that determines whether a helicopter will fly smoothly or violently tear itself apart. Helicopters begin life not as machines, but as raw materials. Giant sheets of aerospace-grade aluminum-lithium alloy are cut and shaped to form the fuselage. Titanium, light, strong, and nearly indestructible, is reserved for the most demanding parts: rotor hubs, transmission housings, and landing gear mounts. Carbon fiber and glass fiber composites are prepared in temperature-controlled rooms. These materials will form the long, aerodynamic rotor blades that slice through the air. Inside the machining hall, 5-axis CNC machines carve titanium components with tolerances of just 20 microns, thinner than a human hair. Every component begins here. Every piece must be flawless. The fuselage, the aircraft's body. One end is assembled in large jigs that hold the skeleton perfectly in place. Workers attach ribs, longerons, and bulkheads, forming a strong but lightweight frame. Aluminum panels are shaped using stretch-forming machines that pull metal across molds with tons of force, giving the helicopter its smooth aerodynamic curves. These panels are riveted into place, one by one. A single helicopter can require more than 30,000 rivets. Sealants are applied to fuel bays and pressurized compartments. Laser metrology systems scan the entire fuselage, ensuring structural alignment within fractions of a millimeter. This skeleton will soon become a flying aircraft.
Bring it down slowly on my mark. Watch the clearance on the starboard side.
rotor blades, the heart of a helicopter's lift, are among the most advanced composite structures in aerospace. Technicians begin by laying sheets of carbon fiber prepreg over a mold. Layer by layer, they build the blade's aerodynamic profile, wide at the root and tapered at the tip with internal spar structures for strength. Titanium root fittings are added to the base of the blade. These will connect the blade to the rotor hub and withstand enormous forces. Once the layup is complete, the entire assembly is loaded into an autoclave, a giant pressure oven that cures the composite at nearly 200 degrees Celsius. After curing, the blades undergo non-destructive testing. Ultrasonic scanners search for microscopic voids or imperfections. Finally, a laser system scans each blade to measure its shape. For a helicopter to fly safely, every blade must be aerodynamically identical. For a Chakordin. At the center of every helicopter lies the rotor hub, a masterpiece of titanium engineering. It must transfer enormous forces from the engine to the blades. It must twist, tilt, and flex, and it must do it millions of times over the helicopter's lifetime. The swash plate, one of the most ingenious mechanisms ever invented, allows the pilot to change the angle of each rotor blade in flight. This is how a helicopter climbs, descends, turns, or hovers. Modern helicopters use elastomeric bearings, rubber-like components that replace traditional hinges. They reduce vibration, eliminate lubrication points, and improve reliability. Each rotor hub is machined, ground, tested, and balanced with extreme precision. Any error here could endanger every flight. The main gearbox is the beating heart of the helicopter drivetrain. Turboshaft engines spin at over 20,000 revolutions per minute. The main rotor must turn at only about 200 RPM. The gearbox performs this enormous reduction using some of the most precisely engineered gears in aviation. Gears are machined from steel billets, heat-treated and ground to mirror-polished surfaces. Each tooth must fit perfectly, with tolerances measured in microns. Oil pumps, filters, and chip detectors protect the gearbox from damage. If a single metal chip breaks loose, sensors alert the pilot instantly. This gearbox is what allows the helicopter to fly safely for thousands of hours.
The backlash looks good here.
Yes, the spacing is exactly on tolerance. We can lock it down.
A little to the left, huh?
Okay, easy now, easy. Looks aligned.
Set her down slow.
A modern helicopter contains miles of wiring, every cable carefully routed through the fuselage. Technicians install avionics racks containing flight computers, navigation systems, stabilization modules, autopilot electronics, communication systems. Hydraulic actuators connect the pilot's controls to the swash plate and rotor systems. Redundant channels ensure that if one fails, the helicopter can still fly. Shielding protects sensitive wiring from electromagnetic interference. Every circuit is tested under load, scanned, logged, and verified. Inside the cockpit, digital displays light up with navigation maps, engine telemetry, vibration analysis, and flight instrumentation. This is the nervous system of the helicopter.
That's seated correctly. All right, the next one is ready.
This is where everything comes together. The tail boom is positioned using laser alignment tools. The landing gear is installed and torque checked. Hydraulic lines are connected. Cooling systems are filled and bled. A crane lowers the turboshaft engine into the fuselage.
Reading
It is bolted
confirmed
to
on the scope.
vibration-damping mounts. Then comes the moment every
Finalizing
engineer
checklist.
waits for.
Looks good to go.
The installation of the rotor system. Technicians carefully lower the rotor hub onto the mast. Each bolt is torquey tightened. Each component is checked again and again. When the blades are attached, the helicopter begins to take its final form.
All right, bring her down slowly, a hair to the left.
Steady, steady. We have alignment.
Secure the connection.
Check complete. Solid connection. Confirmed. It's grounded.
Calibration complete. We have flow.
Roger that. All green.
Rotor balancing is one of the most delicate and most important steps in helicopter assembly. Even a slight imbalance, just a few grams, can create violent vibrations, enough to shake the cockpit, loosen components, or make the aircraft unflyable. Engineers spin the rotor slowly inside a test bay. Laser trackers monitor blade height and position. Accelerometers measure vibration in 3 axes. Technicians adjust pitch lengths, add small balancing weights, and fine-tune dampers until the vibration drops below 0.05 inches per second. This moment determines whether the helicopter will fly smoothly or not at all.
The readings are escalating past amber.
Confirmed. We have a red line event on the main array.
Rotor balanced, the helicopter moves to the ground test area. Engineers tie it down and begin engine run-ups. Hydraulic systems are pressurized. Flight controls are cycled. Fuel systems are checked for leaks. Electrical loads are tested at maximum power. Monitors display exhaust temperature, pressure, torque, rotor RPM, and vibration levels. Every system must pass, without exception. These tests ensure that the helicopter is not just a collection of parts, but a fully functional aircraft ready for flight. And now, the final moment. The pilot releases the rotor brake. The blades blur into motion. The helicopter lifts gently off the ground, hovering steadily for the first time. What began as raw aluminum, titanium, steel, and carbon fiber has become a flying machine. A machine capable of saving lives, exploring remote places, transporting people, and performing missions no other aircraft can. Built with precision, assembled with care, tested to perfection. This is the science of flight. This is the craft of aerospace engineering. This is how helicopters are built.